Good morning, everyone, and welcome to Bite Size Buhl. My name's Mike. I'm the manager of Buhl Planetarium, and I'm joined by...
Hi, I'm Carissa, and I am the producer of the Buhl Planetarium.
Today we are excited to start the countdown and celebrate the launch of the James Webb Space Telescope. This is going to be the most powerful space-sized telescope ever, a collaboration of NASA along with the European Space Agency and Canada. Hundreds of universities, 29 U.S. states, 14 countries, all have worked together for years to create this amazing space telescope. And as of right now, it's slated to launch at 7:20 in the morning on December 25th, this Saturday. Behind me, you can see the famous hexagonal honeycomb shape of this giant telescope. It's plated in gold. Gold is very unreactive, and it reflects infrared light very well. And we'll learn a little more about that and the mission of James Webb. I'm going to turn it over to Carissa now, though, who's prepared a lot of awesome visuals for us. Carissa, take it away.
Thanks, Mike. We're going to take a look at our planetarium software, Digistar. And I just want to give a huge thanks to our friends at the Dome Planetarium at the Peoria Riverfront Museum in Peoria, Illinois. They put together some amazing visuals that we're going to show off here to give you guys a little insight on what the James Webb Space Telescope is about and how it's going to work. So let's get James Webb up here. First of all, the telescope itself is pretty amazing, and there are lots of really cool features to it that are going to let it do some really different things. Now, prior to the James Webb Space Telescope, another space telescope you probably have heard of is the Hubble Space Telescope. Now, the Hubble was launched in 1990, and it has been doing amazing science and observations in that 31 years. But the Hubble Space Telescope was a little bit limited. Now, of course, is groundbreaking for its time, but the James Webb Space Telescope is the next step, and it's going to be able to do a lot of things that build on to the observations of Hubble. So we have Hubble on the left, and we have James Webb right there on the right. You can see they look very, very different from each other. So if we take a look at the Hubble Space Telescope, we can see it has there its solar panels, and we can see that it has a long tube, and inside that tube is where its mirror sits. Now, the Hubble Space Telescope is about the size of a school bus, and it has the mirror inside. And the reason why it was kind of shaped this way is that so they could launch it in the space shuttle. So that's how the Hubble Space Telescope got to space. It was launched in the cargo bay of the space shuttle. Those solar panels had folded up, and it was basically a long tube. Now, because of that, and because of the size restrictions of the, of the rocket, basically, that we had to get it to space, the mirror couldn't really be any larger than it was. So the mirror itself, if it was any bigger, first of all, would have trouble fitting into a good ship, and also it would be really heavy. It would be very, very cost prohibitive to send a very heavy mirror out into space. So that is kind of part of what the James Webb Space Telescope is going to help solve. The James Webb Space Telescope mirror is much larger. And so let's get a look at this awesome array here. So these mirrors are segmented, and that actually is going to allow us to get this telescope out into space in a much more efficient way. So just how are we going to get it into space? Let's take a look. And Mike, feel free to pop in here as well. The coolest feature about the mirrors is that they fold up. So here we can see that folded configuration, so it gets much more streamlined. So we are packing this telescope into the Ariane 5 rocket cargo area, and it's going to sit in that nice little compact capsule. Let's watch that one more time, because we can see how those mirrors will unfold once it gets into orbit, once it gets into its place in space. So this allows us to send it in a really efficient package, and it allows us to send something much larger that's going to capture a lot more light when it gets out there. But where is it going, Mike?
So James Webb is not going to be orbiting the Earth. James Webb is going to be heading to a spot known as a Lagrange point. And what you can see here is the Earth orbiting the Sun, and the Moon is going around the Earth. James Webb will actually be in what's called the second Lagrange point. It's going to be trailing the Earth from our perspective. And a Lagrange point is a location in space where you have a really nice ballet between the gravitational forces of the Earth, Sun, and Moon and the orbital motions of these bodies balancing out. So basically, James Webb will be able to park in that spot, orbit the Sun in a fixed position relative to the Earth and the Sun, and we'll have to expend a minimum amount of energy over time to do any sort of course correction. Turns out there are 5 stable Lagrange points in the Earth, Sun, and Moon system, and they were named for an Italian mathematician who worked this out. His name was Joseph Louis Lagrange. But that's where James Webb is heading. It will be parking essentially behind the Earth in a path that will trail the Earth, orbiting the Sun in that sort of perfect parking space, that Lagrange point. Each mirror you see there is about, well, altogether, the complete array is 21 feet across. Here we can see the sun shield deploying to protect those mirrors. And now that we're in orbit here, we are 1 million miles from Earth. That's where L2, the second Lagrange point, is. We are 1 million miles from Earth, and we are orbiting the Sun.
And this is a great look at just how compact this system will be and all of those components that will unfold to create that final telescope system. So like Mike said, the mirror array is about 21 feet wide. It's huge. And that's going to help capture a lot of light. Because when we talk about telescopes, all of their power rests in how much light they're able to collect. It's very similar to setting a bucket out in the rain. And if you're trying to collect water, the bigger the bucket you have, the more water you'll collect over the same amount of time. So we are essentially sending out this huge space bucket to collect as much light as possible, which is going to allow astronomers to see things that are really far away, things that are really dim and difficult to see. With a smaller tool, we're going to be able to see a lot clearer. Now, another really cool thing about this telescope is how it's going to function, because the James Webb Space Telescope is going to be looking at some really distant and dim objects. And in order to see those, it's a very sensitive instrument that cannot be affected by temperature changes. So we have to really protect this telescope from the heat of the sun, but also the heat of the Earth. And that's what this cool kind of corrugated thing we're seeing underneath the mirror array. All of these different layers are sun shields that are going to protect the telescope from, and its instruments, from any heat that might affect it. We have an image of that too. Yeah, so we can see that sun shield there. And it's almost like layers of reflective material that are going to bounce off all of that radiation and that heat and really keep the telescope safe. So here we can see, get that moved up just a touch. Here we go. So we can see the hot side is always going to be facing the sun. The mirrors are always going to be facing away from the Earth and the sun. So that shield will always be in between the two. So all of the solar panels, the communications, the computer, everything will be on the hot side because those are not quite as sensitive. But we have the mirrors and those sensors on the cold side that are really going to be protected. And we can see on the bottom there, all of those layers are going to keep additional amounts of radiation away. So the first layer is going to be the hottest, and then whatever is left over makes it to level 2, and whatever is left over makes it to level 3. And by the time it gets all the way to the end, so much has been removed. It's a very stable and cold system. So very little heat is going to make it through to the actual telescope.
I think we also have some videos we can show you to get a sense of scale of how big the mirrors and the sun shields are from the clean room, and see a little bit of that action.
Yeah, so here we can see working on one segment of the mirror array.
And those mirrors are made of beryllium, and then they are coated in gold using a technique called vacuum vapor deposition. Just a little bit of gold dusting is coated onto that beryllium and a layer of glass. And gold was chosen because it's particularly unreactive. It also reflects infrared light very well.
And it looks really cool.
Yeah.
Again, we can kind of see the comparison between the Hubble's primary mirror versus the James Webb primary mirror. And it's going to allow us to collect a lot more light. It's going to allow us to do a lot more. We can also see some of the work being done on that sun shield. So it looks kind of like a big sail. It's massive, right? And it's also going to all fold up into that tiny little package. But all of these different layers will deploy to have that space between them that allows it to collect any heat that might get through to the telescope.
James Webb has several missions, and one is to seek light from the very first galaxies that formed close to 14 billion years ago. And we're looking in a range of the EM spectrum known as infrared. I've mentioned a couple times. I think we'll bring up an image of the EM spectrum. You can see that here. Visible light, the rainbow we see, makes up just a very narrow part of this broader range of electromagnetic radiation, all of which is emitted by our own sun and by other stars. Infrared, below red, are waves that are just simply too big for our eyes to see, but Webb will be able to explore the universe in that range. Very distant galaxies emitting UV light, over time that light can be stretched or redshifted by the continual expansion of the universe, and it arrives to us as infrared light. So Carissa, thank you, is circling the infrared side there where we see those very long waves. We can see that rainbow visible light that we can see. And on the other side of visible light is ultraviolet. It's higher than violet. They're very short waves. They're too short for us to see. Light that was once emitted as ultraviolet, as the universe has continued to expand, that is shifted down to the red side and even the infrared side, and now we're receiving it as infrared. And we're going to show you a little difference between viewing one nebula in visible light versus infrared. We're looking at the Carina Nebula. This is a Hubble Space Telescope image. Infrared allows us, as you can see by the side on the right, to peer through interstellar dust and gas and discover more stars, sort of look through that veil of gas and dust and discover more. We use that same technology when we're looking back at our home planet. Infrared allows us to peer through the clouds and study more about agriculture on our own home planet. It allows us to peer through the smoke in a fire and look for heat sources and help save lives. In astronomy, we can look out into space and in the infrared bands be able to look through that gas and dust. A fun way to think about it is using a thermal imaging camera, and we have a picture of a thermal imaging camera here. Here we see a scientist using a trash bag, but when we look at it in infrared, the trash bag disappears and you can see his hand as he's emitting heat there behind the trash bag. So you can think of that as the analogy to peering through that gas and dust out in the cosmos. Using thermal imaging in infrared wavelengths, we can look right through that trash bag and see that heat source there.
Yeah, so the James Webb Space Telescope is going to allow us to see a lot of these really amazing things that otherwise would have been hidden to us. But it's also going to show us a lot of things that we kind of can already detect, but we'll be able to look at them a lot closer in a lot more detail with the James Webb Space Telescope. So one of my favorite things, Mike already knows, one of my favorite things to talk about is exoplanets, and the James Webb Space Telescope is going to help analyze planets around other stars and help figure out what exactly those planets and maybe their atmospheres are made of by using the transit method. So here we're taking a look at what the transit method means. Now, a transit simply means an object moving in between the observer and a more distant object. So we can see a planet moving in between its home star and our viewing perspective. So in this case, it would be the Webb Space Telescope. And so what we're able to see is we're able to measure the light using our telescopes, measuring the light from that star. And as soon as a planet starts to move in front of that star, the light goes down because it's blocking some of that light. So it's reducing the amount of light that's reaching us. Now, if there's multiple planets, we might see that dip even more. Or we'll be able to measure the difference in that dip in light by saying, oh, this is probably a smaller planet because it's blocking less light than a larger one would. Something else that's really amazing, though, is as these planets pass in between us and their stars, is we're going to be able to use the James Webb Space Telescope to actually analyze the atmosphere and break apart the light that we get from those objects and see what they're made of. So just by looking at these systems as they pass through that light from their star, we're going to be able to break apart that spectrum of light, again, using the electromagnetic spectrum, and use the information that sits in that light and see what kind of elements there might be present in atmospheres of these planets. So we're going to be able to determine, could there be could there be life on these planets? Could there be an atmosphere that could sustain life? Perhaps could there be liquid water? All of these things, this telescope is going to be especially made to analyze all this information and really give us a lot of detail that we have not been able to have before. And I think the other amazing thing is it really will build on a lot of missions before it. This mission is not in its own just starting from zero. It's going to build on a lot of missions before it. It's going to build on information we've gotten from Hubble. It's going to look at our own solar system. It's going to analyze atmospheres in our own solar system and take a look at the atmosphere around Mars. And it's going to take a look and analyze the storms on Jupiter and Saturn. And it's going to work with past Cassini information, Cassini mission to Saturn. So it's going to work with all of those prior missions to give us a clearer image of how things formed here, but also how things formed out in space.
Absolutely. I think it's exciting what you said, that it's going to be looking at the universe at different scales and distances. So we'll learn more about our own solar system. We'll be looking at the atmospheres of exoplanets orbiting other stars. And we'll even be looking out at the earliest light from the first galaxies. We're going to show you a quick redshift demo. As we look back almost 14 billion years ago, the farther out we look into space, the farther back we're looking in time. And those galaxies sent out UV light in our direction, but over time, as the universe expanded, that light redshifted. The waves got longer and bigger, and we are now collecting that infrared light today. We're not seeing those galaxies as they look now, but we are seeing them in their primitive states nearly 14 billion years ago. But James Webb will be able to see more clearly than ever and help us fill in that picture of the early universe.
And again, we're not saying that they will be literally red. And a lot of this, in fact, all of it takes place outside of our visible spectrum. That light that our human eyes can see. It's this tiny little sliver right here of the entire electromagnetic spectrum. But space has shifted these things, and time has shifted these things. And that motion is what causes them to slip away from that visible part of the spectrum and into infrared. If we see it red shift, it's moving towards the red side. And if it's blue shift, it's moving towards the blue side. So over here towards ultraviolet. So again, we kind of use these terms and these colors in ways that we can understand because our human eyes can only see some of these colors, some of this spectrum of light. But really, it goes much beyond that. That's what these telescopes allow us to do. They allow us to see more than our eyes can see, and they help translate that information for us so that we're able to observe all of these things beyond the visible spectrum. So this telescope is really going to open up a lot of amazing information to us, a lot of things we've never been able to see before in detail that we've never been able to see it in before. So it's a really, really exciting mission, and it's been a long time coming. And we're finally going to hopefully see it launch on Christmas Day this year. So it's very, very exciting to consider.
Yeah, and it builds on the other telescopes that are out there. So we have that broad EM spectrum, and Hubble, Spitzer, Chandra, all of these other space telescopes, as well as ones on the ground, all have their sort of signature wavelengths or range of wavelengths that they specialize in getting us data. And the James Webb Space Telescope will add to that and help us create a richer understanding of the universe. But as of right now, the launch will be on December 25th. We are very much looking forward to it. And after the launch, it will also take about 6 months for all of the systems to unfold, literally, and calibrate in space. And then we look forward to all the amazing data that we'll be getting in the years ahead from the James Webb Space Telescope.
Yep, and if you want to watch the launch for yourself, absolutely. It's going to be a very historic launch, so get up early. You'll probably already be up on December 25th at 7 a.m. So, but all of that information can be found at nasa.gov. They'll have information about the launch and also more information about the telescope if you want to get your hands on it. So all of that can be found on NASA's website. Definitely tune into the launch if you can, because it has been a long journey to get to this point, and it's only going to get more exciting as this mission really gets off the ground.
So thanks once again to the Peoria Riverfront Museum for these amazing visuals, and to Digistar as well. And Carissa, thank you. Great piloting today.
Thanks, Mike. It was a lot of fun.
All right. Have a great week, everybody, and hopefully we'll be celebrating the launch soon. Take care.